This is BBC Bitesize with Chris Smith and with Richard Van Orden. We're from The Naked Scientists. This podcast is all about the calculations that we use in chemistry. In part 1, we saw how to balance a chemical equation. Well, now we're going to find out how to use them. Richard.
Well, if you know the equation of a chemical reaction and you know how much of the reagents you're using, you'll be able to work out how much product you should get. So if we take an example of burning a litre of ethanol to produce carbon dioxide, we know the reaction equation, which is C2H5OH, ethanol, plus 3O2, oxygen, goes to 2CO2, your carbon dioxide, and 3H2O, the water. The first thing you need to know to start working out how much carbon dioxide you're going to get is to work out the amount of ethanol you've got in moles.
But what's one of those?
A mole is a fixed, really large number of molecules. It's always 6.022 times 10 to the 23 particles of something. It's really an arbitrary number, picked for your convenience, so that a mole of carbon-12 will weigh 12 grams, and this just means that by starting with a massive bucket full of molecules that's a mole, you get sensible gram amounts in the end when you're calculating.
That's all very well for carbon, but here we're talking about ethanol, so how does it work?
Well, the equation tells us that one molecule of ethanol produces 2 of carbon dioxide. 1 mole is a fixed number of molecules regardless of the substance, so 1 mole of ethanol will produce 2 mole of carbon dioxide. To work out the weight of a mole of a substance, you need to know the atomic weight of each of the elements in the substance. Ethanol, C2H5OH, contains 2 carbon atoms, an atomic weight of 12, 6 hydrogen atoms, each with an atomic weight of 1, and 1 oxygen atom with an atomic weight of 16.
So if we tot that lot up, you've got 2 lots of 12, so that's 24, plus 6 lots of 1, that's 6, and 1 lot of oxygen, 16, so that's 46 in total. But 46 what?
Grams. This is why moles are chosen. These numbers will give you the molecular weight in grams.
So how many moles are there in 1 litre?
Now for this you need to know that 1 litre of ethanol weighs 790 grams. You'll have to look that up. And 46 grams goes into 790 grams 17.2 times. So we can see you have 17.2 moles of ethanol to burn.
Right, so you said earlier, from the equation we know, that for every mole of ethanol you get 2 moles of CO2, carbon dioxide, so that means, do I get then 2 times 17.2 moles equals 34.4 moles of carbon dioxide?
Spot on. And as carbon dioxide weighs 44 grams per mole, that's going to give you 1,510 grams of carbon dioxide. You could have done the same thing backwards to find out how much ethanol you would need to burn to produce a certain amount of carbon dioxide.
But carbon dioxide is a gas, so how can it weigh anything?
Well, fortunately we don't actually need to weigh that, which would be quite difficult. Conveniently, it turns out that 1 mole of gas always has the same volume as a particular temperature. So at room temperature, 1 mole of gas always has a volume of 24 litres. So we've got 34.4 moles of CO2. That'll take up 24 times 34.4 litres, 825 litres.
So that's how you work out how much space it will take up. But can we use this for any kind of reaction?
Well, in principle, you can work out how much product any reaction should produce. But in practice, the yield of most reactions isn't 100%. The percentage yield is the amount of product you actually got divided by how much you should have got in theory looking at the equation. This proportion is then converted into a percentage by multiplying by 100.
So if I was supposed to get, say, 50 grams of a product and I actually got 10, what would be the yield then?
It would be 10 divided by 50, which is 0.2, and then times by 100%, so 20%.
So why isn't the yield 100%?
Well, it often isn't possible to get 100% yield. Some reactions convert the starting material into a mixture of different products, and only one might be the one you're trying to make. Or if the reaction's reversible, you might end up with some starting material that hasn't reacted in your solution. Maybe you might make 80% of your product and 20% of something else entirely.
Which would mean under those circumstances the yield was 80%.
Not necessarily. Separating chemicals can be quite difficult, and it's always a trade-off between how clean you can get the product and how much of it you lose. You might be able to get, say, a 60% yield with only 1% of your side product left in. But if you had to have a better purity than that, say less than 0.1% unwanted side product, you might end up losing more product in that process and only getting a yield of, say, 40%.
Are there any ways of doing it better to improve that yield?
Well, sometimes yes, it depends on the reaction, but getting the conditions right, like the temperature or the concentration, is very important.
Concentration, presumably not thinking about it too much.
No, in chemistry, the concentration of a solution is basically how much of something is dissolved in a certain volume of solvent, what it's dissolved in, is usually expressed in moles per litre or moles per decimetre cubed, which is the same thing. So, for example, 1 mole of table salt or sodium chloride has a mass of 58.5 grams. If you dissolve that in a litre of water, you've got yourself a 1 mole per decimetre cubed solution of sodium chloride.
So if you know the concentration, it's easy to work out how many moles you've got.
Yeah, you just multiply the concentration by the volume.
Well, that sounds good. So returning to the yield for a second, is this something that all chemists tend to worry about?
Well, some chemists choose to consider something called atom economy, which is a different way of thinking about how efficient a reaction is. It can be used to compare what fraction of the products would be useful if your reaction gave you 100% yield when you're comparing different possible reactions to make the same product. Lots of chemists work on making big molecules with tens or hundreds of atoms in them, often using a whole sequence of different reactions, putting groups of atoms on or removing others along the way. So it can be useful to keep track of how much material is being lost as byproducts, especially if there's more than one way to make the product and you need to choose between them for an industrial process. Of course, you need to know about the yield too. Even if all the starting material gives a useful product, if your yield is only 0.1%, it's still not a very useful reaction.
So how do I calculate this atom economy for a given reaction?
Well, to take a fairly simple example, if you wanted a water supply on a spaceship and for some reason had to do it by either burning hydrogen or ethanol, how would you choose between them? We said earlier that a mole of ethanol is 46 grams and burning it gives you 3 moles of water. What's the molar weight of water? It's 16 for the oxygen plus 2 times 1 for the hydrogen, 18 grams per mole. So burning 46 grams of ethanol gives you 3 moles times 18, 54 grams of water. Okay, and you used up 3 moles of oxygen to do that. That means you reacted 3 times 32 equals 96 grams of oxygen, 46 grams of ethanol. That's 142 grams of starting material in total. Divide the product by the starting materials and multiply by 100% to get the efficiency. So 54 grams of product, water, divided by 142 grams of starting materials, times 100 percentage, 38%. That's your atom economy.
Well, instead of burning ethanol, what about burning hydrogen instead?
Well, the equation here is 2H2 plus O2 goes to 2H2O. So, in fact, everything ends up in the product, water. The atom efficiency is 100%. So all other things being equal, that does look like a pretty good bet. And in fact, since spaceships tend to carry hydrogen as fuel anyway, they do make their drinking water this way.